He's going to demonstrate that for us. He's going to put a little dragster fuel in there. I'll strike it until I put the cap on. A little dragster fuel in there, put the cap on, and you're good to go. You're going to need to put more dragster fuel in there. No, we're good.
I was like, oh, it's like
Okay. Just make sure the wires aren't crossed. They go to...
Oh my God!
It's okay. I know what you're thinking. Where did the cap go? It's right here. You got it.
Yes, that's
We didn't lose the cap. Yeah, imagine that happening thousands of times a second. That's what's going on in your car.
wow.
So yeah. So methanol has only one carbon, and methanol's big brother is isopropanol. Isopropanol has a lot more carbons. It's a little bit more exotic to balance, but isopropanol is C3H7O plus, again, O2, and it's going to make the same thing, CO2 plus H2O. All hydrocarbons are going to make the same thing, CO2 plus H2O. And we can use our techniques and our tricks to balance this. First technique is, this should be H7OH. First technique is we can rearrange isopropanol from C3H7OH to C3H8O. Make sense? Then we can balance it. So use your crazy techniques that you've learned so far and see if you can balance this. You're going to get some big, big numbers. Well, I try to empty out the water vapor that's in here. Why is there water vapor in there? Because last class, the reaction worked just fine. It's getting there. See a little bit less water in there now. Wow.
Oh boy. Why did you know that? Reggie? I'm sorry.
If you started with my my handy technique of making all the odds evens, then you're halfway there. Because if you make this a 2, and you make this a 2, it becomes a lot easier. So how many carbons do I have over here? 6. Which means this number should be a what? 6. Okay? The only place you're going to see any carbons is in the hydrocarbon and carbon dioxide. So 6 carbons, 6 carbons. How many hydrogens are over here? 16. 2 times 8 is usually 16. So I need to replace my 2 with a what? With an 8. Hey, that's cool. All we have left is oxygen. Neat. So how many oxygens right here in this molecule? 12. How many oxygens in this molecule? 8. Can you see there's 12 and 8? Okay, so 12 oxygens, 8 oxygens for a grand total of 20, which means this side has to have a grand total of 20. How many are in the isopropanol? 2, which means oxygen has to be?
No, it has to be.
It has to be 18, and to make it 18, we'll make it a 9. So the ratio here is going to be 2, 9, 6, 8. Can this be reduced? Can 2, 9, 6, 8 be reduced? No, it cannot. Okay? It looks like it should be because you can divide 8 by 2 and 6 by 2, but you can't divide 9 by 2, so it can't be reduced. Okay, so here's my fun bottle.
Fun ball?
I'm going to put a little alcohol in my fun bottle, a little bit of isopropanol. Now, this thing had a paper gasket. I'm going to see what happens if I don't use the paper gasket. So I'm distributing my alcohol through here, and hopefully there's enough air in here. By the way, what does this feel like? Is it cold, warm, room temperature? Room temperature, okay. It's oily. It's oily.
It's weird. I don't like it.
All right. Everybody think warm thoughts.
Oh.
Oh.
I missed it.
Oh, what is it? Oh, no.
It's alive! Okay, now what does it feel like? It's hot, yeah. It's hot, and you might also notice that there's water droplets that have collected all around the outside. Why are there water droplets inside where the little fire happened?
Water inside?
Because water was made, exactly, water was made, and hopefully it will... No, it'll come back eventually. Yeah, so water was made, and then why did it collapse?
Because the oxygen was trapped. Try to use that.
It took all the oxygen.
Yeah, I took out all the oxygen and I replaced it with very hot water vapor and carbon dioxide. And then that water vapor started to do what on the sides of the container? It started to condense. It started going from a gaseous water vapor to liquid water again, and we're back to normal. All right, cool. And we're going to revisit this idea about condensing and changing in volume next month. But I just wanted to show you that because that's fun. Okay, so that's level 2. How are you feeling about level 2? Okay, so hydrocarbon combustions are by far the most complicated things to balance that we're going to do in this class, but you can do them if you just remember 2 techniques. One, make all your odd numbers even, and then combine, when you have an OH, just combine those. Now, the 4th type of reaction is what happens when you get something kicking something else out. And it's called, well, if you have something and you make something, you basically replace it with something else, that's what's happening. So it's called a single replacement reaction. Can I erase these? So in a single replacement reaction, you have 2 things making up a salt, a positive thing and a negative thing. And then something else comes along that is outside of the compound, and it kicks something else out. So the first one we're going to do is this. I'm going to take some silver nitrate. I love silver nitrate. And silver nitrate is going to be aqueous. And I'm going to add it to some copper wire. I'm going to put some copper wire into silver nitrate. And the silver is dancing with the nitrate, having a great time. Positive silver, negative nitrate. And then the copper comes along and boots it out. You're like, get out of here. I'm more active than you are. Whack. So, fun fact, silver nitrate has to be kept in a bottle covered in duct tape because silver is light sensitive. Anyone have those glasses that get dark outside? You have silver particles embedded in the glass. So add some silver nitrate here. Go. So it's silver nitrate. And into it, I'm going to put, get rid of the bubbles there. Into it, I'm going to put a copper wire. Just like that. And leave it right there. So what happens is the silver is dancing with the nitrate, the copper comes along, boots out the silver, and the silver falls out of solution as a solid. But it does that because the copper replaces it. So the copper was out of solution, now is in solution, and forms CuNO3 2. Copper to nitrate. Well, it does that because copper is more active than silver. Silver is less active. Okay. So this is a single replacement reaction. Copper is out of solution, silver is in solution, copper kicks the silver out and replaces it, and now you can balance it. So go ahead and balance this. It doesn't take a long time, but go ahead and balance it. Once you think you've balanced it, lean over your neighbor and show them your work and see if he or she agrees with you. See you later. All right. Remember the rule about polyatomics? In almost every case, I'm going to protect you from breaking up polyatomics. Okay? Unless I've made a mistake, and I do now and then make mistakes, I've only chosen reactions in this class where the polyatomic does not break up. In other words, the nitrate on this side stays nitrate. Nitrate on this side stays nitrate. So how many nitrates do we have on this side?
6. No, 2.
2. There are 2 nitrates here. How many nitrates over here? 1. So we fix that by doing what? Putting a 2 up here. Now we got 2 nitrates. And how many silvers over here?
2.
How many silvers here?
1.
So fix that. How many coppers here?
1.
How many coppers here?
1.
Are we good?
Yes.
All right. Now, you can already see, and I'll turn the lights on, just in the last 2 minutes, the copper has started to disappear and be replaced with silver. The silver's coming out as tiny little crystals. Here's the one that we did during third period. And it's actually, you can see the copper has gone into solution, making the solution blue. Copper solutions are blue. And the silvers come out in the form of these crystals. It's kind of pretty here. It's like, oh, those crystals. Here it's like, oh, they've all clumped together. But that's what's happening. Now I have another one. And the other one is pretty cool. I've told you a lot about sodium. Now, sodium reacts violently with water. So I'm going to put some sodium in some water. Water is H2O. And it's going to kick something out. But before we talk about what it's going to kick out, we need to talk about water and how weird water is. We've always learned that water is H2O, right? We've always drawn water with an oxygen and a stick with a hydrogen and a stick with a hydrogen and then 2 unshared pairs of electrons. Well, it turns out water is tricky. Water can also be HOH.
What?
I know.
Betrayal.
It can basically be H plus and OH minus. So when you have a situation like this, you look at water and say, water's not H2O, water is HOH. And what happens is you form, what do you think you form? What do you think the sodium kicks out? The H. You're going to form hydrogen gas, which is like that, right? No. Needs an H2. Good. It's diatomic H2. And then what's left is going to be NaOH. And this is going to be aqueous.
So,
This is going to be a gas. Yes. This is a good one. Yes.
so instead of putting H2O, we put HOH?
Yeah.
Okay.
So, and again, the polyatomic hydroxide is going to stay hydroxide. So this is sodium reacting with hydrogen hydroxide. I'm going to enjoy some hydrogen hydroxide right now.
Me too. Wow.
That's some high quality HOH. And it's going to react with hydrogen hydroxide, make H2 and NaOH. Yes?
When do you know when to use H2O and HOH?
Excellent question. The question was when do you know when you need to use HOH instead of H2O when the other side has an OH? Excellent question. Okay, so pretty easy to balance. You look at it and say, all right, how many, be careful here, how many H's do you have on this side?
3.
No. Remember, this is hydrogen hydroxide. Only 2. This is hydroxide. Polyatomics stay together. So hydrogen, sodium, hydroxide. How many hydrogens do you have on this side? 2. How many hydrogens do you have on this side? 1. So we're going to put a 2 up here. Now we have 2 hydrogens and 2 hydroxides. We're going to slap a 2 over here so we have 2 hydroxides, and a 2 over here so we have 2 sodiums. And this has been going on for the last few hours. If you look at the fume hood, you'll actually see a column. And in this column, fume hood's over there. You see this thing. That humid. Yeah. So in this column, do I want to turn this? Yeah, why not? Let's just go ahead and turn this around. Look at that. Boop. Oh, I'm on your notes. That's okay. So, yeah. So in this column, there's pieces of sodium that have been floating around. This is mineral oil, and in the bottom is water. And what happens is the sodium falls to the bottom in the mineral oil, touches the water, reacts with the water, producing hydrogen bubbles, and up they come. Isn't that cool? And this has been going on for like 4 hours. So the sodium will float to the bottom, touch the layer of water, and hydrogen comes up, and the sodium carries it up a little bit, carries up, or basically buoys up on the hydrogen bubbles. And it just keeps going and going and going. And this purple stuff, this tells you there's sodium hydroxide in there. Okay. This will just go forever. So I'm going to go ahead and set this right here. And we're going to do it outside. Only we're going to do it a lot faster. My tray is still out. Right? Okay, remember how in a second. You are going to need to wear glasses because we always prepare for the worst, although sometimes we don't anticipate students wearing polyester and fire catching them. That is, I'm not excited. That's the first time that anything like that's ever happened. Hopefully I'll get a phone call from a parent. Hopefully Wagner will back me up. But so remember how we talked about sodium? Sodium is an alkali metal. What is one of the properties of an alkali metal?
Shiny. Hey Alexa.
It's malleable, and it's super malleable. So remember how I said before that sodium basically has, it feels like Play-Doh? It really does. It feels like Play-Doh. But it's definitely metallic because if I scrape away the top layer, it's shiny, which is pretty cool. So I'm going to basically make two pieces here. In case the first one doesn't go, I'll have another one ready to go. What we're going to do is we're going to go outside in just a little bit. Oh, by the way, it's funny how they ship you sodium. This comes in a big aluminum bag, and it's filled with sand. And then the bottle comes in another bag in the sand. Yeah. Then they put all of that in a big box, and they fill the box with sand. So in case something happens and the bottle breaks, the sodium will basically be trapped in here in multiple layers of sand. Okay, so this is what we're going to do. We're going to go outside and get some water. And I'm going to put the sodium in the water. You're going to need to back up. And the first thing that's going to happen is the sodium is going to react with the water and heat up and melt. And it turns into a little ball of liquid sodium. While that is happening, there's going to be hydrogen being given off. If the reaction is hot enough, the hydrogen will catch fire and light on fire, have a little ring of fire. If that gets hot enough, the sodium will explode. Yeah, you're like, oh, I hope it explodes. Okay, so let's go outside, grab some glasses, and head outside. Hey, can someone grab the camera too, please? Yeah.
Grab the camera.
Reggie.
I'm so mad that we don't.
Look, I'm vlogging. Say hi.
It's very easy.
So it's up to the vlog.
Hey, Sean, say hi to the vlog.
Joe. Oh, I got my
Sunny, stop.
Where is my acid?
He's gonna watch this during his like, oh my goodness.
Of course it's always son.
Great.
Show the vlog giving me kicks.
Oh, I look stupid.
Someone light me on fire.
Someone light me on fire. I want to see
Real
if
quick.
I'll
Wow,
explode.
the camera girl.
It's the vlog. My vlog.
Okay, so first and foremost, everybody's recording. So first and foremost, this is an acid-base indicator. We're going to talk about acids and bases near the end of the year, but just know that solutions can be acidic or basic or neutral. The greenish color tells you it's basically neutral, it's just the water that came out of the tap. kind of neutral-ish. Yeah, that's disgusting. Anyway, I'm gonna add some sulfuric acid to it, and the sulfuric acid turns it pink because acidic solutions are pink. So now it's mildly acidic. So the first thing I'm gonna do is I'm gonna drop a piece of sodium in again. It's gonna melt. Then the sodium is going to heat up, and if it's hot enough, it'll light the hydrogen gas on fire. Notice it's making purple. Come on, get hot. Everybody think hot thoughts.
Me.
There it goes. So now it's lit on fire. You think it's really hot.
He's the chosen.
Eamon, the smoke went to you.
I go me at like
Back off. So let me add some more acid here.
Dude, that's
So this piece is twice as big as the previous. Is this seeing the floor? It is. Okay. Good job. Good job with that. So this piece is twice as big as the previous piece.
Don't stop twitching.
Me?
Dude, what if it just fizzles out?
No.
Are you thinking hot thoughts?
me. Oh, we got it. We got it.
Hey, there we go.
Oh, that was perfect.
Oh,
Yeah.
fire babies.
That's what I was hoping to happen. Here,
Fire
have another piece.
Bruh. Is this stuff edible?
Very no. Yeah, very no.
Very no.
Excruciatingly no.
It might. There's not a lot there, so
It just
if it
looks like
explodes,
a
it won't explode. I think it fell through the.
Floor's on fire.
Yeah, I think the pan has a hole in it.
Yeah. Wait, so you know how like our stomach has acid or whatever?
Uh-huh.
So if you ate a piece, would you like explode?
No, your throat would seize far before you were actually able to swallow it. The reaction with the saliva in your mouth would be pretty violent.
What if you just put it directly in your
Okay. Okay, let's go back inside.
Sorry.